It's important that we understand measurements in the way that scientists think of them. When we record a scientific measurement, we do so in a very precise way, a very specific and consistent way. So we report all the digits that are certain, and the last digit is estimated, because there is uncertainty in any measurement. You can't really say this is exactly 1 inch long, or that's exactly 2 kilograms. Like, yeah, but the balance is 2.0000. Well, there is uncertainty in every measurement, and how closely you know the measurement depends on the tool that you're using to measure it. And so scientists measure things and report those measurements to indicate how precisely they know the measurement. So here we have an example of some carbon monoxide concentration measurements. So 1990 through 2010, we see the carbon monoxide change from 8.9 parts per million to 2.1 parts per million. Over here, this is written in a different form. Now we're taking these numbers and those are being rounded. If we look at these measurements, we're assuming that there's uncertainty in this last digit. The scientists always assume uncertainty in the last digit. So when we look at these numbers, we would say that these are plus or minus 1 part per million. That it's about 9, meaning it could be as low as 8, could be as much as 10. There's some uncertainty in there. We're going to call it 9. Over here, the last digit is in the tenths place. So that implies that the uncertainty is in the tenths place. So this means 8.9 tells a scientist that's between 8.8 and 9.0. Take that number, subtract 0.1, add 0.1, that gives you the approximate range. There's some uncertainty, but this number is much more precise than that number. And we always want to write our numbers in a way that reflects the actual measurements that we made. Like if you say there's 440,000 people in Fresno, do you mean there's exactly 440,000 people in Fresno? That you counted them all? I mean, even if you did go count them all, somebody's going to be born or die and change that number, right? There's uncertainty in that because it's a large number of people. When we say the distance between Reedley and Fresno is 30 miles, do we mean exactly 30 miles? No, we mean approximately, right? So we deal with uncertainty in numbers in our everyday lives. In science, we are just more careful about how we specify the numbers. And so it's important to understand the last digit is always understood to be uncertain. So the number of digits that we record depends on the measuring device. This is a very important idea. Read between the lines. And I will get on you in lab about this. Read between the lines. There is information between the lines. So let's look at this balance here. This is like a kitchen scale, right? What is that? Looks like a pistachio. So if we're going to use grams, because ounces are stupid, ounces are English, we see here that this is between the 1 and the 2. So we are certain that it is at least 1 gram, right? Because it's between 1 and 2. It's more than 1, it's less than 2. It's 1 point something. We're certain about that. But if we write 1 gram, that implies that we're uncertain about it. So in between here, we see, well, it is definitely less than 1.5. We're going to estimate between the lines. And what we do for most things is you mentally divide it into 10 spaces. Halfway would be 0.5, and you just mentally divide it. Is it going to be perfect? No. It's an estimate. There's uncertainty. You just do the best you can. But we look at this guy, and we might say, I think it's 1.2. So a good recording of that mass would be 1.2 grams, because that tells us the uncertainty is in the tenths place. We're not certain of the 0.2, but we are certain of the 1. It's more than 1. We're certain of that. And so we record one uncertain digit. So the rule of thumb here is to estimate 1 decimal place past the smallest division. So on this scale, we have divisions. The lines each represent 1 gram, because here's 0 and here's 10. And in between are 10 spaces. So each line is 1. That means we estimate to the next decimal place. If you're using a ruler that has divisions, lines of 0.1 centimeter, then you estimate to the next decimal place. On a thermometer, if it's got 1 degree markings, you estimate to 0.1. And I call that reading between the lines. So the precision of a measurement depends on the instrument. We record the measurement to reflect the instrument that we used. Now, when we take that measurement and we do math with it, we do calculations, funny things can happen. You can end up with a whole bunch of digits when you divide something by 3, for example. And so we want to avoid, well, let's make up an example here. Let's say I had something that was 4.7 centimeters long. And I'm going to divide that into 3 pieces. So I'm going to take 4.7, I'm going to divide it into 3 pieces, and my calculator says, oh, that's dumb, I'm not going to do it that way. My calculator says that's 1.5666. That each of those 3 pieces is that long. Does that mean if we take a piece of, I don't know, maybe this is copper, piece of copper metal that's 4.7 centimeters long, there's uncertainty in this tenths place, right? When we measure that, we're telling you it's between 4.6 and 4.8. There's a little uncertainty here. If we take that and we divide it into 3 equal pieces, that now we know it to the nearest, I don't even know what that digit is. Is that reasonable? No. Because we didn't even know the length of the first piece that closely. We only knew it to the nearest tenth. So the best we could possibly know this is to the nearest tenth. So when we do math with a measurement, we have to have some way of keeping track of the uncertainty. And the way that we do that in general chemistry is through significant figures or significant digits. Have you guys heard of significant figures? How many people hate them? Okay, yeah, that's pretty typical. Usually the majority of the class not had a good experience with significant figures. The alternative, though, is to use differential calculus on all the calculations. Anybody want to learn that instead? I didn't think so. I don't even want to go back and remember that stuff. Significant figures is a shorthand method of keeping track of error so that when we do calculations, we don't end up with a ridiculous number of digits like this. So there are some rules that we have to learn. What we call a significant figure, these are the non-place-holding digits in a recorded measurement. They include all the certain digits and the estimated digit. So in this measurement, 4.7 centimeters, the 7 is estimated. There's always one estimated digit at the end. The first estimated digit, the first uncertain digit, is a significant figure. and everything that comes before that. So we would say that this number has two significant figures. The greater the number of significant figures, the greater the certainty of the measurement. And so here we're going to go through some of the rules. It's the zeros that mess people up. The first rule is easy. All non-zero digits are significant. So if we look at this number, 13.301, we're here, the bolded numbers, they're talking about what is included in this rule. Well, the 1, the 3, and the 1, those are non-zero. Anything that's not zero counts. Okay? Over here, this number, 0.00421, the 4, the 2, and the 1 are non-zero digits. Okay, that one's easy. It's the zeros that mess people up. No end of trouble with zeros. Because there's three kinds of zeros. There are interior zeros, there are leading zeros, and there are trailing zeros. So there are zeros in the middle of the number. Those are interior. There are zeros at the beginning of the number. They lead the number. And there are zeros that come at the end. Those are trailing zeros. So interior zeros are always significant. So here, 3,403. This zero is an interior zero. It's trapped between non-zero digits. So those always count. And over here, this number has two interior zeros. Doesn't matter whether they're before or after the decimal point. They're stuck between, right? Leading zeros come at the beginning. Leading zeros are not significant. Never. All they do is hold the decimal place. Here, 0.00023. We made a measurement. This 3 is uncertain. The 2 is certain. These zeros are just holding the decimal place. Are they important? Yes, they're very important, but they don't reflect a measurement. So let's think about the number 5. So there's the number 5. If I put a 0 in front of it, does that change its value? No. Does it look weird? Yeah. But I can't count this 0 as a significant figure because I can put 1 0 there. I could put 3 zeros there. The number is the same. Those are not reflecting measurement. Leading zeros, these zeros are important because they hold the decimal place, but they don't reflect a measurement. So leading zeros never count. Numbers, zeros at the beginning. So the trapped ones always, the leading ones never, and then those trailing ones. Okay, so I'm doing this a little differently than the textbook explains it. The outcome is the same. So if you like my version, don't confuse yourself with the textbook version. If you don't like my explanation, go with the textbook version. So this is how I think about it. Trailing zeros are significant if there is a decimal point written in the number. Anywhere. A written decimal point. So we look at this number, 39.0. This is a trailing zero. It comes at the end. There's a decimal point. 120.00. There's a decimal point. These are trailing zeros that are significant because there's a decimal point. Trailing zeros before an implied decimal point are ambiguous and should be avoided. So a number like 300, there's no written decimal point. But we know that the decimal point would be right there if we were going to write one. We know where it is. But those zeros are just holding space, just like leading zeros. They're holding a space, so we don't count those. 238,100. No decimal point. They're ambiguous. And so what we do with the ambiguous numbers, we can't tell if they're significant or not, just based on looking at the number. So we're going to assume the worst. We're going to say, well, we don't want to assume that this number is more precise than it is, so we're going to go with less precise. We'll assume those zeros are not significant. Now, an interesting thing happens when you put numbers into scientific notation. In scientific notation, what we're doing is we're factoring out powers of 10 so that we get the number between 1 and 10. So this has an implied decimal point here, and we're going to move the decimal point 2 places. 300 is equal to 3 times 100, which is the same as 3 times 10 to the 2, right? What happened to those trailing zeros? Do we need them anymore? No. When we write numbers in scientific notation, these ambiguous trailing zeros go away. The problem goes away. If we take a number like this 39.0, 39.0 is equal to 3.90 times 10, right? Or times 10 to the 1. As this number was written, did we have to write that 0 there to preserve the value of the number? No. If we wrote 39, it would still mean 39, right? But because we wrote the 0, this is telling us the uncertainty is in the tenths place. If we write the number 39, it's hard to point to that. Now the uncertainty is in the ones place. It changes the uncertainty of the measurement. So we can't do that. We can't just get rid of that 0. So we carry that 0 along with us into scientific notation because this is an estimated digit. That's an important number. It's significant. It reflects measurement. It's these trailing zeros that mess people up. That 0 was not necessary for holding the decimal place, for keeping the value of the number. Anytime you see a number like 300, 100,000, population of 440,000, it's most likely sort of an estimate, right? 440,000. You think, well, it's probably between 420,000 and 450,000. It's probably not to the nearest 10 people. Any questions? Either I just made it so clear that you all get it, or I've just completely lost you. And that's the trick. I never know what it is till later. And then we have something called exact numbers. And in terms of significant figures, we consider that exact numbers have an unlimited or infinite number of significant figures. So how could you get an exact number? If you have exact counting of discrete objects. I have a pair of sunglasses and a pair of lab glasses. How many pairs of glasses in my hand? 2. Is there any uncertainty in that? No. I can count my children. 1, 2, 3, 4, 5, 6. Is there any uncertainty in that? Is it possible that there's 6.3 or 5.8 children? No. It's exact. Now, exact counting. Can you count the population of Fresno exactly? 440,000. So that's the number I remember. I think it's changed. You can't exactly count that many people because people die. During the process of counting that many people could die, people could be born, people could move away, people could move in. You counted one block and 2 hours later some family moves in and messes up your number. So counting numbers, we have to be a little careful because counting discrete objects work as long as the number is relatively small, and there's this gray area Well, what do you mean by relatively small? So counting of numbers. Integral numbers, that means integers, whole numbers, that are part of an equation. Okay, the diameter of a circle is twice the radius. That's an equation. So the diameter equals 2r. This is an integer in an equation. That's considered an exact number. Defined quantities. Some things are defined. A foot is defined as 12 inches. That is an exact number. Anytime you're dealing with units within one system of measurement, within the metric system or within the English system, those numbers are exact. Some conversion factors are defined, others are not. When you go between the metric and the English system, safest to assume that it's not exact. One of the exceptions is the inch and centimeter. That is exact. And in the table where you find these things, if it's exact, they'll tell you it's exact. So let's look at these and identify the number of significant figures in each of them. So 0.0030 liters. How many significant figures? 2. Leading zeros, not significant. This is a trailing zero. There's a decimal point in the number, so we count that. So we count the 3 and the 0. How about that next one? 4. All of the zeros here are at the beginning. Leading zeros never count. 4, 7, 1, 6, we count all of those. How about number 3? 4. How about number 4? Okay, I heard 2 different answers, and they're both acceptable. I heard ambiguous and 3. These zeros here, trailing zeros without a decimal point, we can't be sure. It's ambiguous. If we're forced to decide, we're going to say they're not significant, and we're going to call that 3. 29 pencils. I heard a mumble, but I didn't understand it.
2.
It's not 2. Infinite. Can you count exactly 29 pencils? Most people can. Andrew, not so much. He's only 5. He gets confused when he gets to 17. But most people can count 29. That's a small enough number, discrete objects. How about 53,069 milliliters? 5. The 0 there is trapped. How about this guy down here? 4. Yes?
Can you explain again how that makes it infinite?
Okay. Why does 29 pencils have an infinite number of significant figures? Because there is no uncertainty. You count out the pencils, there's exactly 29. There's not 28, there's not 30, because you can't have part of a pencil, right? When you measure the length or the mass or the temperature or the time, you can have fractional bits. But when you count discrete objects, you either have 1 object or 2, you don't have 1.5 objects. So 29 pencils, exactly 29, we could say there are 29.000, and we could spend the rest of our lives writing zeros. And so we say it's infinite. Any other questions? Questions are good. So now we need to learn what to do with the significant figures in the calculations. So when we do the calculation, we want our result to reflect the precision of the measurements that we got the result from. We're not gaining or losing precision just because we did some math. So there are two basic groups of calculations. There's multiplication and division. Those are opposites of each other, and they share the same rule. And then there's adding and subtracting. Those are opposites of each other, and they share the same rule. So if you're multiplying or dividing, your answer, the result, will have the same number of significant figures as the factor, the things that you started with, that has the fewest. So here we've got 1.052 times 12.504 times 0.53. And the calculator is going to give you a number like this with some extra digits. When you do your math and you're showing your work, go ahead and write them down. You can write them all down. That's fine. Then to find out how many significant figures you should actually report, you're going to look at the numbers you started with. And you're going to say 1.052, that has 4 significant figures. And this one has 5. This one only has 2. And then, this is so hard. What's smaller, 4, 5, or 2? 2. So we're going to go with 2. So we're going to take this 6.7, we're going to keep the 6 and the 7, we're going to drop the 2. And the rounding rules apply. So 2 is less than 5, we just chop everything off, and our answer is 6.7. Here we're dividing 2.0035 divided by 3.20. Your calculator will give you something like that. Some of that is garbage. You look at the numbers that you were doing the math with. This one has 5, this one has 3. So then this 3 is smaller than 5, so we're going to round our answer to 3 significant figures. So 0.626, the next digit is a 0, so we chop it off. You don't look at the 9, you don't start at the far right end and round up and down all the way through. You just look at the first digit that you're chopping off. In adding and subtracting, the rule here is when you write something out, it often sounds more confusing than it actually is. The result carries the same number of decimal places as the quantity with the fewest. Well, it's helpful to look at an actual example. So here's this number, 2.345. Where is the uncertainty in that number? The 2, the 3, the 4, or the 5? 5. The last digit's always uncertain. So in 0.07, which digit is uncertain? The 7. And in 2.9975? The 5, right? So you can go ahead and do this on your calculator, because we all have brain farts that cause us to add things up wrong. But if you had to do this using just your head, you would take this 5 and you're adding it to what's in that spot? 0. Could be something else, though. We don't know. We're so uncertain we can't even estimate what's there. And how about what's up here in this spot? We are completely clueless. So, is this 5 that we get a certain number or an uncertain number? That's uncertain. And then the next column, here we've got 5 that has uncertainty in it, and we have to assume 0, but we really have no clue, and a 7 that we're certain of. When we add those up, we get 12, but is that too certain or uncertain? It's uncertain, because one of the numbers that we added to get it was uncertain. So now we come to this column. 4, that's a certain digit. We're adding an uncertain 7 and a certain 9. And we come up with, what, 21? Is that 1 certain or uncertain? It's uncertain because of the 7. The 7 was involved. If that was actually an 8, this number would be different. So there's uncertainty here. So let's get to the 10th place. A 3 that's certain. Are we certain about this 0? Yeah. We don't call it a significant figure, but we know it's 0. And a 9 that's certain. And when we add those and get this 4, is there any uncertainty in the 4? No. So we do the math, and then the things to the left of that are all going to be certain. when we have a measurement or the result of a calculation involving measurements, we keep the certain digits, the 5 and the 4, and the first uncertain digit. So we're going to keep the 1. So 5.41 is the proper way to express that sum. Because the rest of this really doesn't matter in light of the uncertainty in this one. So that's what the rule means. We're looking here, this has uncertainty in the 3rd decimal place, this is in the 2nd, and this is in the 4th. This has the fewest number of decimal places, 2 decimal places, so the answer will have 2 decimal places. And there's another example over here with subtracting. This one has 1 decimal place, this has 3 decimal places, so our answer has 1 decimal place. Multiplying, dividing, number of significant figures. Adding and subtracting, number of decimal places. They're different. Now, sometimes in life, we know, okay, it would be best if we could do this. It'd be great if I could go 100% at whatever project, but you also have life going on, and very few of us can pay all of our attention to one thing, right? So sometimes during the class, I will tell you, okay, this thing is more important than this other thing. The multiplying dividing rule is more important to know than the adding and subtracting. Try to learn both of them, but the multiplying and dividing is more important. I think we have some examples. Rules for rounding. Round down if the number is 4 or less, round up if it's 5 or more. So if we're rounding 5.37 to 2 significant figures, that would be we're keeping the 5 and the 3. The number we're dropping is a 7, so we're going to round this up to 5.4. Because 5.37, we have to choose. Is this closer to 5.3 or 5.4? It's closer to 5.4. Let's do this last one, 5.349. So 2 significant figures, we're keeping the 5 and the 3. We're dropping the 4. We completely ignore the 9. Don't even look at it. People do crazy things. 4. The 4 is less than 5, so we drop it, and it rounds to 5.3. Sometimes we have multi-step calculations. You have to multiply a bunch of things, and there might be adding and subtracting and multiplying and dividing all rolled into one messy equation. We want to avoid rounding errors, so we wait until the end to round. Do all your math, come up with the final answer, and then round it off. Now, I've also taught Chem 3A a lot, and in Chem 3A, I'll say, well, if you just have a real hard time with that, go ahead and round as you go along, and that's fine. But this is real chemistry now. Okay, this is Chem 1A, and I want you to do this. Carry along extra significant figures until you get to your final answer. And we'll see this in lab, where we measure things, and we do this, and we do that, and we combine all these things. And you want to wait until the very end to round, so that you avoid rounding errors. Because if you round every step, that can sometimes mess up your answer. So how do you go about doing that? Well, let's look at this example. So here we have numbers multiplied, and here's a subtraction. Well, we have to understand orders of operation. This has to be done first. When we do this subtraction, we get 0.479. Now, this number has 2 decimal places. This one has 3 decimal places. So if that was all we were doing, we would round that to 2 decimal places. What we're going to do is we're going to underline the last significant digit in that intermediate answer to remind ourselves this number only has 2 significant figures. But we're going to leave the other digits alone. We're going to leave them there. We're going to let them come through the calculation, and we'll round at the end. Now we have 3 numbers. To multiply, we can do all of that together. The calculator gives us this answer. And now we look, this one has 3, this one has 4, and this one has 2. 2 is the smallest, it limits the answer. So sometimes you have to write down some intermediate values. Examples. So this first one, just adding, 45,900 plus 10.49. Do it on your calculator and write down what it says. I'm getting 45,910.49 meters. We're supposed to round the answer to the correct number of significant figures. Well, in this first number, 45,900 meters, where's the uncertain digit? Is it the 0? Or is it the 9? What kind of zeros are these? Those are trailing zeros. Is there a decimal point? No. These are ambiguous. So we have to assume that they're not significant. So that's going to tell us the 9 is uncertain. And in the 10.49 meters, which digit is uncertain? The 9 also, right? Because it's the last digit. Now, our rule that we talked about for adding and subtracting was the number of decimal places. But how many decimal places does 45,900 have with uncertainty in the hundreds place? Well, that's a little confusing. Let's stack them and add them and see what happens. So this 9 was uncertain, and we added it to something we know nothing about. This 4 we're adding to something we know nothing about, so that's uncertain. Remember, this 0 is uncertain. We're certain about that 0, but this guy's still uncertain. Here's another 0 that's just a placeholder. We don't know what the value is. Plus the 1, that's got to be uncertain also. This 9 has uncertainty, and we're adding it to this unwritten 0. That has uncertainty as well, doesn't it? There's different ways to think about the adding-subtracting rule. Really, it comes to which one has the greatest uncertainty. The uncertainty in the highest decimal place. This is uncertainty in the hundreds. Hundreds. This is known to the nearest 100 meters. This is known to the nearest 100th meter, 1 over 100. This error is much bigger, the uncertainty. In fact, when we add 10.49 meters to 45,900 meters, it doesn't even make a difference. Because it was already an estimate of plus or minus 100 meters. What difference does 10 meters make? It makes nothing. It's like a semi-truck full of ping pong balls. And you pull it through the truck scale and you have it weighed. And you throw one more ping pong ball on there. Is that going to matter? Is the mass of the truck going to change? Not significantly. You go back on the scale, it's still going to give you the same number because that truck scale does not measure to the nearest tenth of a gram, right? Probably measures to the nearest 10 pounds or something. Okay, so the uncertainty in this number is at that 9. How do we round this off to the correct number of significant figures? Can we call this 459 meters? Please say no. It's like, okay, I'll pay you $45,900 a year to do this job, right? But we're just going to round it off to $459. Would that be good? No. When you round a number, when you round off those insignificant figures, you round to the correct number of significant figures, you can't change the magnitude of the number. You can't make it lots bigger or lots smaller. So this is where scientific notation comes in. So here, we need to round to the hundreds place. If you're rounding to anything, any place left of the decimal point, you should put this number in scientific notation first, and then round it off. To put a number into scientific notation, we look at where the decimal point is, and we move it over so that it's after the first non-zero digit. So it was here, I moved it 1, 2, 3, 4 places. So that's 4.591049 times 10. The exponent is the number of places you moved it. Whether that exponent is positive or negative depends on whether this is a big number or a small number. Is this a big number or a small number? It's a big number. Would you like to have $45,000 in your wallet? I would. Would you have positive feelings about that? Yeah, that's a positive number. If it's a little number, a little paycheck, you have negative feelings and it's a negative exponent. So there's the number in scientific notation. We know we need to stop at the 9. Now we can chop digits off without changing the value of the number. So this is 4.59 times 10 to the 4th meters. Scientific notation is great because it gets rid of all the pesky zeros. There's no leading zeros. There's no insignificant trailing zeros. All the zeros that are there are important and significant. Skip to number 3. Well, no, we should do number 2 as well. Okay, number 2. If you don't have your calculator out already, get it out. So this is 29,412 divided by, if you have forgotten, you need to relearn how to use scientific notation on your calculator. This part here, times 10 to the, that's the EE button, or you might have an EXP button. So I'm going to put in 29,412 divided by, and then I'm going to type in 5.10 EE 3. No, times 10. The EE does it for you. And press the equal sign. And I'm going to have to run this over here, so I don't have enough room. This is what my calculator is showing me. Anybody else get that? If you're not doing your scientific notation correctly, what will happen is your decimal point will end up being 1 place over. And that's an indication that you're using scientific notation incorrectly. So how many significant digits should we report in this answer? 3. This number has how many? This has 5, and this one has 3. In scientific notation, it's only the coefficient part. The times 10 to the something, those are the place-holding zeros. We just pulled them out. So we've got 3 on the bottom, 5 on the top. So we go with the smaller number. So it's going to be 5.7. We're keeping the 6. We're dropping the 7. 7 is 5 or greater. We have to round up. 5.77. What happened to the units on that? They canceled. Milliliters over milliliters. Poof, they went away. It happens.
it doesn't have units?
It doesn't have units anymore. It can happen. It's relatively rare in chemistry, but it can happen. And when it does happen, you should go, huh? And go back and double check sometimes. So number 3, whenever we have adding and subtracting mixed together with multiplying or dividing, you got to be careful. So I'm going to take the 16 and subtract the 1.448. When I press divide, nothing happens on my display because my calculator has an understanding of order of operations. I need to be smarter than my calculator. I know that because of how this is written, the subtraction needs to be finished first before I divide. So I need to press the equal sign. The display then changes to 14.9041. Now I can divide. Otherwise, I'm going to end up with the wrong answer. Anybody else get that answer? I'm using you guys as my second calculation. Anybody having trouble getting their calculator to show them that answer? I'm really good. I'm the calculator whisperer. I can make your calculator behave. Okay. So we get our answer. Then we have to look at the sig figs. So we've got subtracting here. We have to look at the result of that individual operation. 16.3521 minus 1.448. That part was 14.9041. It's my children calling me. They can wait a minute. So this is the result of this subtraction. How do we determine where the uncertainty in this number is? We look at the number of decimal places, right? Here the uncertainty is in the 4th decimal place. Here the uncertainty is in the 3rd decimal place. So 3 decimal places. So this should have 3 decimal places. The uncertainty is right there on the 4. This number was then divided by that number. How many significant figures does this number have? It's got 5, because the 1 is not significant. So this one has 5, this one has 4. So then our answer should have 4. So 1, 2, 3, 4. We're going to go to the 3. 2.10, you have to round up, 4. And what happens with the units there? We're going to end up with centimeters. Here we've got centimeters squared minus centimeters squared. That's going to give us centimeters squared. Divided by centimeters, it's going to give us centimeters. Isn't this fun? Some of you are like, yeah. Some of you are like, no, it's not. Okay, so do this one and tell me with the correct number of significant figures what the answer should be. Anybody want to volunteer an answer?
Is it 1?
It's not 1.
Number of sig figs?
The answer expressed with the correct number.
than 4?
Nope. Yes, 4.16.
Why doesn't the 1 over 1,000 count?
That's a very good question. So in the units here, the milligrams canceled out. 8 grams per cubic centimeter. When we look at these numbers, this 1 only has one significant figure, it appears, and this 1,000, we would, by our rules, I'm pointing in the wrong place, the 1,000, we would say only has 1. But this is a relationship between grams and milligrams. That is exact. A gram is exactly 1,000 milligrams because of how the units are defined. This is a conversion factor within the metric system. So we would say that those have an infinite number of significant figures. And what that means is that we can just not even think about them. That's a conversion factor within the metric system. We just leave that out. We do it in the math, but when we think about the significant figures, we don't even have to consider those. So then we're down to this guy, which has 3, and this guy has 4. So the 3 significant figures, we end up with 4.16. So these sorts of calculations and these ideas with the significant figures are going to require some practice, aren't they? One of the beautiful things about mastering chemistry is that you get instant feedback. You do the problem, you find out immediately if you got it right or not. If you didn't get it right, you get some more chances. It'll deduct partial points for every time you take a stab at it. But you can still get points even if you missed it the first 2 times and got it right the 3rd time. So you can learn as you go along. If you're working a problem and you've tried it a couple of times and you've looked through the textbook and you've listened to that part of the lecture and you're just like, I don't know what I'm doing wrong, send me a text message. What I can do, even on my phone, is I can actually go on Mastering Chemistry and I can see the answers that you have put in. And a lot of times by looking at your incorrect answers, I can figure out what mistake you're making. In more complicated problems where there's work to be shown, it's really helpful if you take a picture of your work and send it to me. And that way I can look and see what you're doing. And I'll ask you questions. I don't feed you the answers, but I'll ask you questions and I'll get you going in the right direction. Oh, this is a section that never ends. Precision and accuracy. These are 2 terms that can be kind of confusing. Accuracy refers to how close the measured value is to the actual value. It's like hitting the bullseye. How close to the bullseye on the dartboard is this measurement? Precision refers to how close a series of measurements are to one another, or how reproducible they are. Let's see if we have an illustration. Oh, sort of. So here we got 3 students weighing a lead block. We know that the lead block has a mass of 10.00 grams. So here's student A. He's weighing it 4 different times, and these are the numbers that he gets. He comes up with this as an average. Here's student B and student C. So if we look at their averages that they came up with, which average is closest to the true value? Student C, right? This guy's off by 0.01 grams, and these 2 are off by more. This result is more accurate. The average answer that he got is closest to the true value. It's the most accurate. But if we look at the variation in these numbers, 10.49, 9.79, this guy's all over the place, isn't he? This guy, I don't know why I'm assuming they're guys. All of these numbers are pretty close together. And this one is kind of scattered around a little bit, but not too bad. These 2 students have pretty good precision. They make the same measurement over and over again, and all the measurements are close together. This guy's got poor precision. He's sloppy. This student has good precision but poor accuracy. which means that there may be a systematic error. If you measure something and you've got your thumb on the balance, or if your instrument is calibrated incorrectly, you're going to have this error that's the same every time. And so even if your measurements are very precise, they're very close together, they could still be off by a lot, be very inaccurate. So here, it's kind of hard to look at those numbers and see much. That's why scientists graph things a lot. So here's student A's numbers graphed. Here's the true value in blue and the average in the pink dashed line. And this guy was actually more accurate than this one, because this pink line is farther away. But this one is more precise. These are all close together, and this one is accurate and precise. Accuracy and precision often go together. Not always, but often. So there are two basic kinds of error. Random error, and that's one that has an equal probability of being too high or too low. And so we often will take multiple measurements, because then the random error cancels itself out. Sometimes it's high, sometimes it's low. The more measurements we take, the more the error cancels out and the better value we get. Systematic error is an error that is more consistent. It's either too high or too low most of the time. And so it skews your answer, it makes your answer or your result not accurate.